I'm Harrison Schmidt, Apollo 17 lunar module pilot.
I'm Chip Shearer from the University of New Mexico.
I'm Clive Neal from the University of Notre Dame.
Well, there are three types of samples that were collected on the surface of the moon that are being examined by this ANGSA program, or the Apollo Next Generation Sample Analysis Program. And these were samples that were collected by Jack from Station 3 during one of the Apollo 17 traverses. And this was a double drive tube. And Gene Cernan hammered this double drive tube into the surface of this landslide deposit that was derived from the South Massif. And the lower portion of this drive tube was placed within this core sample vacuum container that was sealed on the surface of the moon. And then a third type of sample that was analyzed by the ANGSA program were the frozen samples that, upon return from Apollo 17 in December of 1972 and January of 1973, they were placed in a freezer and kept frozen at, I think, minus 25 degrees centigrade for 50 years now.
I think it's very important to recognize that already some of those new technologies have benefited the analysis of those samples. For example, we can see inside rocks, inside cores now that we couldn't do 50 years ago. And that means that we can make decisions, much better decisions on what to analyze. A good illustration, Apollo itself stimulated new technology in analytical chemistry, mass spectrometry, and the like.
Oh, the microbeam techniques, and Chip, you've run a microbeam technique, the SIMS lab. The development of SIMS and in situ age dating on these samples, we can now be informed of where to go within these samples, how to cut them, then how to then properly plan out the analyses from those data. It's emphasized by the Apollo 17 orange glasses. They were collected in 1972, and it wasn't until 2006, 2007 that it was shown that they actually contained water that was in the interior of the moon that was brought up in these glasses, and that comes from the microbeam techniques. And because those samples had been well curated, they were still available to be used. Yeah, the maturity, understanding how long that regolith sample has been exposed to the solar environment on the surface of the moon is critical for understanding the changes that weathering has made on those samples.
The interesting thing about this core that you mentioned, Chip, is that it's seems to be penetrating two avalanches. There is a young avalanche that covered an old one. The old avalanche is probably maybe on the order of about 96 million years exposure, but actually occurred about 150 million years ago. The new avalanche appears that it may have, again based on these maturity measurements, as well as a cosmic ray exposure age on one of the boulders, that it was exposed about 56 million years.
Well, the other thing that we need to think about here is what caused the avalanches. Was it impacts or was it movement along the Lee-Lincoln fault scarp that has been mapped out?
My inclination is that it's probably movement along the fault, because now because of the Lunar Reconnaissance Orbiter camera images we can see that there have been, since the basalts fill the valley floor, there have been 4 major mass wasting events off the South Massif. The South Massif that we mentioned is 2,100 meters high, over 7,000 feet. It's really, and it's a very steep slope, probably 26, 27 degrees on the average is the slope. And so it doesn't take an awful lot to get this so-called regolith, this debris layer that covers the slope of the massif, to start to move. And there is a thrust fault called the Lee-Lincoln fault that crosses the valley, and there is, I think, very strong evidence that at least the young avalanche was triggered by this movement along that fault. The moon has started to contract. It's cooling. whereas for most of lunar history it was expanding due to the generation of radioisotopic heat. Now that has moved to the point of where it's contracting, and as a sphere contracts, it's going to move over itself. The surface will move over itself.
Yeah, we're starting to see more evidence for modern day lunar tectonics. Saw it during the Apollo era with the Apollo seismic network.
These type of ridges that cross the moon in many different places have been known for a long time. Prior to Apollo, we knew that these ridges existed, but we didn't understand them. They were called wrinkle ridges and things like that. But now, I think with the evidence we have from lunar reconnaissance orbiter images, and also just by having had a chance to drive over one of these scarps and see what the evidence is on the ground, that these are indeed thrust faults that are altering the character of the surface. And now we can go back into the seismic data collected on the Apollo seismic network and start to identify events that are registered in those seismic things as these kind of thrust faulting events. It's an indication of how important synthesis is to bring various types of data together and try to see what they're telling you in aggregate rather than what they're telling you just in isolation.
And so what's very unique about the ANGSA program is what it does bring is people who work on samples and look at samples using new technologies, but also it brings in people who study the moon remotely, geophysicists, and obviously somebody who's had boots on the ground that brings a personal observations to the ANGSA program. And integrating all of these observations.
Yeah, moonquakes are something, as you know, I'm sort of interested in a little bit. If we did in fact penetrate the second layer underneath the youngest avalanche deposit, the samples don't go down as far as we would like, but they go down quite a ways.
You can never satisfy a geologist.
No, you never can. We always want more samples, but I think that what we've learned, during and after Apollo, is now helping us put this into a much bigger picture.
Well, and operationally, it's important because, as you pointed out in the past, Clive, some of these moonquakes are significant quakes, and that design of any kind of settlement or operational buildings or equipment has to take into account that they may encounter a quake of significant magnitude.
The significant magnitude, the maximum ground motion lasts for up to 10 minutes. Not just 30 seconds, 90 seconds as we get on this planet, because the moon has what they term a higher seismic Q value. So when it vibrates, the energy is not deadened, it just keeps moving.
Yeah, that was one of the first things that we learned from the Apollo 11 seismometer, was that if the moon gets hit by something, that energy continues to cycle around the moon. Almost any sample has a story to tell. So all of the samples, the Apollo samples that have been collected, and not all of them have been fully studied, unfortunately. These new samples are important, not so much more important than any other sample, it's just that we can gather more information about them, and it also is telling us what we need to do to go back to get information out of the old samples, and how we apply these new technologies to samples collected in the past, and also to samples collected in the future.
Also, what's really clear from the core samples is they represent material from the South Massif, which is very, very difficult to sample. And so essentially this landslide deposit brings this material to the valley floor where it was sampled. And within this core, we now have brand new samples that we haven't been able to that we haven't seen in other parts of the Apollo collection. So these are new and somewhat unique samples. Some of them are referred to as magnesium sweet rocks, which all have a story to tell with regards to the internal characteristics of the moon, the characteristics of the crust, potentially the characteristics of the mantle.
through the last 15, 20 years, one of our colleagues, Lars Borg at the Livermore Laboratories in California, has been gradually, systematically getting really very precise analyses of the age of these magnesium sweet rocks. And they're starting to coalesce on a single age, about 4.35 billion years old. That is very interesting, that if there was indeed, as he refers to it, as a magmatic event 4.35 billion years ago on the moon, what was that event? And that's one of the big new questions that we will be looking at as we look at more magnesium sweet samples from this core. I personally think it's what it's recording is a giant impact on the moon, namely the Procolarum impact. And some of the other samples from the Taurus Littrow area that I collected also are starting to indicate that maybe we have, because of that very large impact, actually sampled the deep mantle of the moon. The dunite from, again, from the South Massif, the Boulder 3 at the Station 2 that we collected there, the troctolite from Station 6 that was part of the rake sample from Station 6. Both of those tend to indicate a rapid change in pressure as they were brought up from deep within the moon. And that change in pressure may well have been the result of the excavation caused by this large Procolarum impact. When I say large, the basin, the Procolarum basin, is 3,200 kilometers in diameter, and so that's big, even for on the lunar scale.
I think looking at those samples, again, putting that in context of what we now know, it does allow us to make big interpretations from itty-bitty little samples that come out of a core tube.
The core that we're looking at, it's 70 centimeters long. It does record in its individual components the history of the sun over some significant period of time. We have another core that's 3 meters long that we took at Apollo 17 at a site near the Lunar Module Challenger's landing point that gives us even more of a record. And when one starts to look at the isotopic composition, particularly of nitrogen in that core, something that was measured back in the early 70s, we start to see evidence that we can indeed start to read the history of the sun, at least as it relates to the ratio between nitrogen 14 and nitrogen 15. And what we call a del 15 ratio shows that possibly about 500 million years ago, the sun went through over a factor of 2 increase in the energy of the solar wind. Now, what else was happening 500 million years ago? Here on Earth, we were going through what's known as an explosion in the diversity and quantity of life in the oceans of the Earth. Is that related to this factor of 2 increase in energy from the sun? More than likely. It's always been thought that the Earth actually warmed during that so-called Cambrian explosion period when life became more abundant and more diverse. But we never had direct evidence. Well, with a little more work, we may have actually direct evidence from the moon that indeed the sun did give us a warmer Earth. The other aspect of, and maybe one of the most important aspects of the entire Apollo effort, is that we have begun to fully understand, I think, what that environment, as you referred to, Clive, that environment of the early Earth was like. And it was extraordinarily violent. But it was violent here on Earth in a water-rich environment. And it is in that environment we also now know that life started here on Earth. And so piecing that together is going to be a very, very important part of the science from Apollo.
We can learn a lot from Apollo on how to collect samples on the moon, and basically how to understand what the true solar wind content of the regolith is. And this is something that we tried to do with the ANGSA project, is to analyze that headspace gas. And in the core.
Some of the preliminary analyses suggest that the core sample vacuum container does contain a lunar component within the gas. Again, this will need to be submitted to other labs for other measurements to be made, but this will be a real breakthrough in better understanding what the volatile concentration characteristics are of the regolith. That's really critical and important to us to understand the interaction between space and the moon's surface. Also, what we ended up doing, what was very unique about the ANGSA program, is that the ANGSA program developed a new methodology to opening up this core sample vacuum container. During the Apollo program, there were only 2 core sample vacuum containers collected, one during Apollo 17 and one during Apollo 16. Neither had been opened since before the start of the ANGSA program, and then the program enlisted Washington University, St. Louis, to develop a collection tool to collect this gas, and the European Space Agency developed a piercing tool that we could pierce this container and sample the gas. So we've developed 2 new approaches that weren't in existence during Apollo to open these sample containers. These will be useful for the Artemis program.
And not only that, it is in these solar wind volatiles that we really have the resources that will ultimately support lunar settlement and potentially support longer trips to Mars. The solar wind is primarily hydrogen, as a matter of fact, protons, but as they come and hit the moon and they become hydrogen gas in atomic form anyway. But helium is there, helium-3 is there, which is an interesting potential fusion fuel here on Earth. If you have hydrogen, you can produce oxygen from the regolith just by heating it. It turns out to be very, very important for potential use in what we call cislunar space and a variety of applications for propulsion. One of the new samples that was kept frozen is one from underneath a boulder that has been in continuous shadow for at least 65,000 years. There's some discussion of whether it was longer than that or not. And that sample in itself is the first time is a sample we can look at to try to understand what permanent shadow really means at the poles. And that work is starting to come through thermal luminescence analysis and that kind of thing.
But we need ground truth, because these are all orbital data that we've been looking at. And coming back to the technology that ANGSA's developed to analyze these gases that can evolve in these vacuum-sealed core tubes, this is something that could become routine if you have these types of collections done by the Artemis astronauts. And they're at the poles to see whether or not it's not only in these very cold regions, but around these cold regions that some data seem to suggest. So gathering these types of samples in vacuum by Artemis around some of these permanently shadowed regions could be very, very important for understanding the true potential of what is exactly there that could one day be transported back here to make life better on this planet with clean energy. We have a completely new view of the moon, because during Apollo, the moon was bone dry. Now we find there's a water cycle on the moon. And there are other volatiles that are on the moon that are cold trapped at the poles, but also there's day-night cycles on the moon of volatiles on the lunar surface. One of the passions I have at the moment is a lunar resource prospecting campaign. What is up there? How much exactly is up there? So we talk about, there's a lot of talk in NASA about using the polar water ice resources because there's billions of tons of that. We don't know that. We don't know that. Now, we could generate a cislunar economy if there are billions of tons, and this country says we're going to have a permanent human presence on the moon, then it gives the commercial sector, oh, we've got a long-term partner there that is going to make our investment pay off, not right away, but we can invest in it because there's a long-term future. There's this new thing that the Science Mission Director has called Commercial Lunar Payload Services. Fixed price contract, we'll take your scientific payload to the moon for X amount of dollars. And I contacted those companies and got their hiring statistics. So in 2019, there was over 100% job growth in these companies. 2020, when everything was contracting, it contracted, and there was only 66% job growth in those companies. This is high-paying, high-tech jobs. It's a new sector of our economy that's within our grasp. It enables commercial participation so that the taxpayer investment that is made through NASA grows these industries, and it gives a feedback loop to this planet, which makes society better on this. Helium-3 is what I call a long-term product because we don't have sustainable fusion reactions. There are multiple minute sustainable fusion reactions being done in Korea and China. We need to sort of catch up because it's happening, because it's gone from millisecond to multiple minutes in about a decade. And that's what I found is you can't just be a geologist. You've got to understand policy, you've got to understand economics, you've got to understand engineering. And so I say there's always something new to learn.
Economics.
And Chip's brought the ANGSA to the forefront by his dogged persistence, let's put it that way.
One can find deposits that are unique, but are they economic? Will they allow humans to essentially live off the land on the moon? That we don't have to get supplies from the Earth of oxygen or water. The resources are there. But we need to find out, is there enough, what state they're in, and how do we process them? That's an important next step that I think ANGSA provides us with a step in that direction. Also, a very important aspect with regards to the ANGSA program was training of the next generation of scientists, sample scientists, geologists, engineers. We have the ANGSA program is a program which is multi-generational. It goes from Jack, who's been just so incredibly great with these young professionals. His enthusiasm is just incredible. So there's a broad spectrum of people involved in ANGSA, and allows us to train these individuals for the future and make the real link, generational, multi-generational link from Apollo to Artemis. We brought in early career people and mid-career people and some older career people.
That's you.
to really interact with the processing of these samples. This will be critical for when the Artemis program occurs and new samples come back. We will have a new generation of professionals with experience.
We have new technologies that have primarily come out of the private sector that have to be integrated into what can be done within the government sector. The three of us are really a bridge to the previous generation of people that trained us and that were deeply involved in Apollo, a bridge to the new generation that has to carry it forward.
What is gratifying, though, is to see the enthusiasm in that Artemis generation. They want to learn, they want to understand about the moon, and I think they also want to see the 13th human walk on the moon. I mean, 50 years since Apollo 17 in December. So this is now time where that generation can have their Apollo moment.